live right now, folks. There we go. So what I'm gonna do today, folks, is I'm gonna go through a number of problems here from the section on compositions, and some of them towards the end will be a little more abstract, but it's important to understand those because you won't need that much of the chain rule for this particular class, but this will be crucial in calculus 2. So if you take calculus 2 and you don't know the chain rule, then you're going to struggle there big time. The chain rule again so they need this abstract understanding of a chain rule in calculus 2. So that's kind of what trips a lot of kids who actually take calculus 2. That's in a situation like this when you had Calc 1 in spring and then there's a summertime when most people don't do anything. And then they go back in the fall and they don't remember the rules. So then it's really difficult. It's Calc 2 is already a little higher than Calc 1. And that's kind of what catches a lot of people. So remembering the chain rule, it's very, very important. And I'm gonna insist on that. So there's gonna be questions on the test. There's gonna be questions on the quiz with a chain rule. So you cannot avoid that. And I'm just gonna make sure that you really know it for Calc 2. And in case you forget it, it's possible. As I said, summertime is long. You will have an easier time because we use the same book for calculus 2. You'll have an easier time at least. You come back to this section and you remember what we did. And I'm gonna leave these videos online as well. So in case you ever need to review the lesson on the chain rule, then you can just go online. As you noticed yesterday, we had a small technical issue, kind of randomly happened right in the middle of a lesson, and I broke it down. But it was a lucky thing because I broke it down and I wrote the title on YouTube. So the first part was some applications and of trigonometry, and the second part was exactly that, the chain rule. So look at the introduction of that, and that's the next lesson today. We're gonna go and reinforce those issues. So those problems that we discussed last time. So let's get started here, folks. If you have any questions, do let me know. I want to get started here with yet another review of the chain rule in a slightly different form. So usually the chain rule, remember yesterday we said if we have two functions, f circle g, the composition of two functions, like we did in the review sessions, at the beginning of a semester, we had a bunch of review lessons and we discussed about compositions and such for this particular reason. So when you calculate the derivative, you will get f prime of g times. So this is the composition here. This is times as in the product times g prime. So that's the way people write the chain rule. But in the book, and I forgot to mention that, and it's important to understand, in the book they say d over dx. So they use this kind of language of f circle g of a composition of two functions, and they say, and pay attention here because this is interesting, they say df over so df over dy, because f would be a function of some y, times dg over dx. So they say that, and it's a little unclear here because the variables, so remember f would be a function of, would be f of y, and x will be, g will be a function of x. So why do they use these things? Well, so it gets a little bit confusing if you look in the book. So I think this is a clearer situation, a clearer expression. So over here they also say of g. So it's a bit unusual, I would say. But there is a better way of saying things, if you simply call your g of x will be the thing that I'm going to substitute in for y here when I do the composition f of g, right? Because when I do the composition of f of g of x is f of g of x, so it makes sense to denote this g of x to to call it y. And in that case, there is kind of a simpler way, sort of a mechanical way to remember this chain rule, which will say that d over dx of f of y, remember g is called y now. All right, is equal to df over dy times dy over dx. And this leads some people to thinking that, well, it looks kind of like simplification. So yeah, it would make sense to say, if you formally cancel out these two, dy, dy, you would get back d over dx. So it kind of makes sense to say that. But be careful with these formulas. So again, we are going to use this when we do implicit differentiation, but just be careful there. So so let me again. So this is kind of a complement of theory. So let me now go and go back and treat some concrete situations. So here's what I'll do. Again, you don't really have to remember much of what I just said. Again, it's a bit of theory, and the important thing is to be able to apply things, to recognize things in practice, the chain rule, and that's going to be the focus of today's lesson, to kind of, look at the practical situation and figure out, oh, what's going on here, which one is the composition, and how do I apply the chain rule. That is key, folks. So, the theoretical formulas will come to you as soon as you understand kind of how to manipulate things here mechanically. So we really focus on the mechanics of applying the chain rule right now. So that's number 7 of 2.5. We're going to go back to the theory, so we're going to do some theoretical questions a little later. But the number 7 of 2.5 says you have this function f of x equals 5x to the 6th plus 2x cubed. Everything would be to the 4. So how do you do the derivative of this particular function? So now let's recognize the situation here. So look at that. That's going to be my, if you remember, that's going to be my y if you want. So I'll say, when I do, if I just had simply y to the 4, right? So this quantity, I'm going to call this quantity, this one here, that's a composition of two functions, you recognize, right? So that's the 4th power, and inside that I put the y. So if I had y to the 4, I would say the derivative is simply 4y cubed. But what's missing here? So remember, we said that that's just f of f prime of g. So this is what it is. F prime of g is 4y cubed. But we also need times, and we need times g prime. So the guy that's in here, which is times y prime in my case. So it looks kind of neat to write it this way. And then all you have to remember is you have to remember what y is. So y in this case was, remember, y was 5x to the 6th plus 2x cubed. And when you work with that, you will say, oh, so that's 4 times that, 5x to the 6th plus 2x cubed times, which is cubed, right? So it's cubed here times, and then you'll say y prime. But y prime is this guy primed, which is also in x. So that's going to be 30x to the 5th, right? Because it's 6 times 5x to the 5th plus 6x squared. So this is going to be the final formula. Oops, sorry about that. There we go. So this is going to be the final formula. You can leave it as a product like that. You don't have to write it out. It's always going to be some sort of messy formula. So make only cosmetic changes if you need to. All right. So this is this here. You can in the book, for instance, they would factor a 6 and they would factor x squared and stuff. I don't care about that. So when we get there, if we ever need it, we will do that. But for the time being, that's sufficient for me. So I'm hoping that this example, captures the essence of the chain rule for you. This example number 7. This is a pretty good problem, and I'm gonna do number 8, which is in the same spirit, folks. So number 8 here again. If I were in a classroom face-to-face situation right now, I would say, here we go, folks. Take 2 minutes to look at number 8. Now let me know if you can do that. So if you did that, and we would work it out on the board. However, over here, so again, I'm gonna assume that you will do that at home when you buy. If you rewatch the video, you will see that. So what's f of x here is 1 plus x squared to the 99th. And you do the exact same thing as before. So remember, we can call this guy y, and this then looks like y to the 99, right? And the derivative of that, remember, the derivative, the important thing is that the derivative ends up all in x. You don't want to keep y in your final answer, right? The final answer should be still in x. So when you do the derivative, folks, f prime is going to be the derivative of y to the 99, which is 99y to the 98, right? And then times, and I'm going to say times y prime, because that's what the chain rule tells me that I have to do, that times y prime. So I'm kind of, paving the road for implicit differentiation. We'll do that in implicit differentiation as well. So this is f prime, folks. And at this point in time, because I know the y's, there's a y and y, same y. So this is 99 times, and y was 1 plus x squared. So the underlying quantity here, folks. Not to the 99, just by itself, right? That's to the 98 times. Then y primed is this guy primed, which is 0 plus 1. So that's going to be just 1 plus 2x. Yes, Tyler. Tyler, do you want to tell me something, or just inadvertently turned on the mic?
Oh, I didn't know my mic was on. Sorry.
All right, no problem. So folks, this is the final answer to our question. All right, so please go home. When you go home, do number 7 and 8 and 9 and so on. These are homework problems. Do them independently at home and watch a video again to make sure that you know how to do those. All right. Okay. So we're gonna move on to the next page, and we're gonna do problem 9. So problem 9, so we're going to spend time, understanding the chain rule here. So problem 9 from 2.5 is the following: f of x equals the square root of 5x plus 1. And before we do anything to this problem, again, let's recognize the pattern. So let's go back to, so remember here, square root of something, right? What we had before was some expression to the 4, some expression to the 99. So let's do the exact same thing here. So let's write this as 5x plus 1 to the 1/2, folks. So remember, the square root is the 1/2 power. So now, folks, I want everybody to remember when we do these sort of things, we do it with a goal of rewriting the problem in a calculus friendly way. So using powers like this is called a calculus friendly way. Using square roots is not particularly friendly. Likewise, using denominators, so we have to have rules to kind of avoid those. Well, that's one of the rules here. So this is not the answer to the problem. This is just the exact same problem rewritten. But now I can say, oh, you know what? This looks like y to the 1/2. if I make this notation 5x plus 1, this sort of, it's called substitution, it's going to be called later. So if I do that, then, you know, that's, that to the 1/2. And I can say, well, then f prime is 1/2, right? So I'm looking here, 1/2 times y to the negative 1/2. Everybody should know that. And then times y prime, remember, times this guy here. And that is easy to substitute and we find out the final answer. So it's 1/2 5x plus 1 to the negative 1/2, and then times, and y primed, y is here 5x plus 1, so y primed is 5. And these, it's kind of nice to combine them a little bit. So 5.5, 5/2 times 5x plus 1 to the negative 1/2. All right, so this is the final answer to this problem. Now, if you have any questions, folks, again, I hope these problems that we did up to this point are shedding a clear light of what's going on. You know, when you deal with a derivative with a chain. All right, so I'm gonna do one more problem and then I'll do some. I'll make a remark. So it's number 10 of 2.5 is a problem in the same spirit. So it says g of x equals 2 minus sine x to the 3/2. And again, I may sound like a broken record, but it's the same pattern as before. Is something to the something else. So it's a power, folks. So recognize this pattern. This is the pattern that we'll recognize when we have the chain rule. You will find other patterns later on in calculus too. So that's why I'm saying that, that's why I insisted on that theoretical part, because what people they tend to sort of understand this pattern, memorize this pattern, and then they find out in calculus too, oh, that's not what we did in calc 1. Well, you did that, but there weren't enough examples to show other patterns other than just powers like these. So all these problems you can see, this is a power, the previous one was a power, look at that, and the previous one was a power. So all of them were powers basically. Likewise here, I have a power, so what is it? It's y to the 3/2. What is y in my case? It's 2 minus sine x. So still a power of y. And then it goes by the same rules. So g prime is going to be 3/2 times y to the 1/2. Why is it 1/2 here? Because it's 3/2 minus 1, folks. So right, remember the power rule? All right. Then times, we're going to say times y prime. And this is going to be 3/2 y to the 1/2 times. And this y prime here, you know what? Y to the, come on, y to the 1/2. So 2, okay. So let's say let's say not y, folks. Let's say what y is 2 minus sine x, right? To the 1/2 times, then y prime is 2 prime, which is 0, and then negative sine x prime, which is going to be negative cosine x, because sine x prime is cosine x. All right, so this is going to be the final answer. You can pull out the minus sign in front of the formula. That's okay. We don't need to do that. So I'm going to leave it like that. Now, these are the examples that I wanted to cover here, and we cover them with a little bit of speed again because we don't want to. I don't want to leave gaps during the recording, but it's a good point. This is a good point to stop, to pause for a second and say, you know what? How about this function? So let's look again at this example. F of x equals x to the 7th. How do I do f prime? You know, why not do the exact same thing that I did earlier with a chain rule? So I'm going to call this y. So I'll say y equals x. Then this is y to the 7. So x is, just relabel x, right? Y to the 7. And then the derivative with a chain rule. The derivative is going to be 7y to the 6 times y prime. Now let's see, do we get the exact same thing? Because we know that the derivative of x to the 7 is 7x to the 6. Do we get the exact same thing, folks? Well, let's take a look at that. So it's 7 times, we know that y is the same as x, so it's x to the 6. And trick here, folks, y prime. Y prime is 1. Is the derivative of y with respect to x. That's just 1. So it's times 1. So this really, you retrieved 7x to the 6, so you don't get anything new if you apply the chain rule like that to our function f. So it's just the exact same thing. So I want everybody to understand that the chain rule doesn't do anything bad to your formula. So the worst case scenario, you end up by making a very complicated substitution, a very complicated selection, because in some problems it's not so obvious what the substitution should be. And then you're going to end up with some really messy formula, but it doesn't do any harm to your problem. So, all right. And finally, I'm going to do a problem here that is slightly different from the ones we did up to this point, and that's going to be number 11. So now pay attention to number 11 here, folks, for a second. So number 11 of 2.5 says here's a function f of t equals, and I'm going to have a fraction here, 1 over so what is it, cosine t plus tangent t. Oops, tangent t. All right, there we go, and that's squared. All right. So by the way, that function I just look now carefully is called a of t. All right. So how do we do the derivative of that? So where is the power here? Well, there is a power too, except that the power is negative, which is okay, folks. So again, if you want a calculus-friendly way, what you want to do, you want to rewrite this as, and let me see, do we have one at the top? Yes. So you want to rewrite this as, and you say cosine t plus tangent t to the negative 2. And right now you recognize the pattern we worked out, we did here very carefully with the power. That's a negative power. That's okay. So we are going to do the exact same things as we did earlier. We're going to call this y equals cosine t plus tangent t. We're going to call that y. The function is y to the negative 2. So the derivative is going to be, so let's write it this way here. So y to the negative 2, the derivative a prime is going to be negative 2 times y to the negative 3 times, right? The negative 2, the exponent, you drop it by 1. Negative 3 times y primed. And all I have to do is to substitute things around here. So negative 2 times y. Y is cosine t plus plus tangent t. Well, this is a bad idea to put t's here like that. So this is just tangent t here. So to the negative 3, right? Negative 2y to the negative 3 times. And y primed itself is negative sine t. Remember, cosine primed is negative sine. And plus secant squared t. That's because tangent primed is that. So these are the derivatives of cosine and tangent. All right, this is our final answer for this particular problem. I want everybody to understand that most of these questions here are just simply that, are powers of some complicated expressions. And you want to break them down and recognize those powers. I'm going to do one more example. This is a slightly more sophisticated question. Again, we don't have to go to this level of sophistication. Even if you're a math major, you'll rarely find questions like, let's say, number 41 or 42. Well, we'll do one of those. So, I'm going to do something like number 19. Number 19 is a good example of, combining rules. So number 19 of section 2.5. All right, h of t equals t plus 1 to the 2/3 times 2t squared minus 1 cubed. All right, so this is h of t. And this is a problem that is very interesting, because the first thing that comes to mind, I have a bunch of powers here. I should probably apply the, maybe the chain rule somehow. But yeah, you do. But before you do it, you gotta take care of a product here. So this is a little problematic. So the product rule comes first, folks. This is one quantity, this is another quantity, this is a product of those powers. You want to do the product rule first. So h prime of t goes first by the product rule as the quantity t plus 1 to the 2/3. Oops, and I wrote 3/2. Don't do that. All right, come on. Okay, to the 2/3. So this one prime times, then you'll have 2t squared minus 1 cubed prime. Oh, is that correct what I wrote? No, not correct at all. So, so I made the freshman mistake. So the freshman mistake is doing what I did here. So I wrote the product of two things. I wrote the first one prime times the second one prime. Nope, not at all correct. So, so it's going to be the first one prime times the second one unprimed. So 2t squared minus 1 cubed without that prime sign, plus, and then it's going to be the first one, t plus 1 to the 2/3. All right, there we go, times, and then there's going to be the second one prime, 2t squared minus 1 cubed, all that prime. So, so now we take care of these separately. So this one here, take care of that. So it's going to be 2/3 times t plus 1 to the negative 1/3. 2/3 minus 1, folks. So this is, by the way, this is the chain rule here. So so it's that power, remember? So y to the 2/3. I forgot to write y here, but I should have done that. So 2/3 y to the negative 1/3 times y prime. Now y prime, because this is the y here, is t plus 1 primed, or I'm going to write it that way, t plus 1 prime, so everybody understands where it came, the formula came from. And then times, this guy stays the way it is, so 2t squared minus 1 cubed. All right, so that's plus. And then over here, we have t plus 1 to the 2/3 times. And then you have this guy prime, which is like again with a chain rule for here. So it's 3 times 2t squared minus 1 squared times, and this is one of those few times where I'm going to say times what, folks? Can you write me in the notes, because this is easy to write the answer here. So what quantity am I saying times here? So if you can write me in the chat the answer here, this is one of a few times, and again I want to check that everybody follows here. So the derivative of this guy here, where my mouse is right now, goes here. So let's see, what do we have here? So so this is the derivative. The derivative is these two, that and that. What do I need to put in here, folks? I'm going to wait for somebody to write me in the chat. All right. Okay. So let's see. So correct. That's correct. Very good. So 2t squared minus 1 prime. But tell me what that is, folks. So indeed, over here, I have to put 2t squared minus 1 prime. And I'm going to do that. And now tell me what these are, folks. So when I simplify, I get 2/3 times t plus 1 to the negative 1/3 times over here we said we get 1, right? So we can ignore this essentially and say just, skip over it's 1 times anything is just that thing, 2t squared minus 1 cubed plus, and then I have t plus 1 to the 2/3 times 3 times 2t squared minus 1 squared. How about that? What's this thing? 2t squared minus 1 prime, folks. All right, so there we go. So there's a bunch of people here. 4t, very good, very good. So excellent, folks. So 4t. So now you see, this is a point where I can be sympathetic to the folks in the book. The authors of the book said, don't leave it like that. Try to simplify. Could you? Yes, you could simplify this one. Why? Because you could, for instance, take out a factor of 2t squared minus 1 squared from here and from here. And in fact, you can even operate on these at the level of these fractional exponent here. Now, I'm not going to bother you with that because that's not so important. It's testing your pre-calculus or college algebra skills, and that's not the goal of this class. But if you're curious, if you look in the book, you will not see this answer. You'll see probably a different answer. If you're curious how that is reduced, this one is reduced to that one, let me know. And if you want, I can show you how to do that next time. But I don't want to spend my time with that here. So again, we covered essentially everything that's possible out there in terms of the chain rule. Now, I want everybody again to understand it's all about powers here in this class. Most of our functions will be where most of the situation where we will apply the chain rule will be powers like that, some complicated expression like this one here, 2t squared minus 1 cubed, and you do derivatives. All right, so there's other situations though, and here's an example. So this is a super complex example. I'm not going to worry much about that. So let's do number 41. So these are difficult, challenging examples, folks. Number 41 of 2.5. We'll do them though. So once you understand the structure of the problem, they're not terrible. So x plus square root of x. So what do we need to understand here? We need to understand that we have a bunch of powers here, and we need to write the powers nicely. And once we do that, we will recognize the main pattern of our problem. So the main pattern of our problem, I said something, I did something else. So first of all, the quantity x plus square root of x is simply x plus x to the 1/2. So that takes care of what's inside here under the square root. Now, it's under the square root, so this itself is got to be to the 1/2. So you see how that can be written nicely. And now I think it's transparent. What I had here, of course, is the same as what I have here, but this is much better for calculus purposes because I can say, you know what? I recognize that pattern, y to the 1/2, where y is x plus x to the 1/2. So really, I can do, and you have a y here. So I should have said a different letter. I don't know, or some U or something else. So let me put a different letter, folks. Sorry about that. I don't want to confuse you here. So let's put a different letter. Again, I don't want to make the confusion between y and this y, which is the name of our function. So this is u to the 1/2, let's say, where u is this expression. And when I do the derivative, y prime is 1/2 times u to the negative 1/2, right? Because that's how you do the 1/2 power derivative times u prime. And that's very easy here to see now. That's 1/2 times, let's get rid of this stuff here. So 1/2 times u to the negative 1/2. Well, u was x plus x to the 1/2. All of that will be to the negative 1/2 times. And u prime is this one here. So 1 plus 1/2 x to the negative 1/2. So that's the derivative of u. That's here. All right, and that can be, again, that can be simplified if you want. You can say, well, over here I have 1 over 2 times, and I can put these revert things now. I can put here square root because I had x plus x to the 1/2 to the negative 1/2. So the square root of x plus x to the 1/2, which is x to the 1/2 is itself square root of x. So there we go, that's that times, and over here I could say 1 plus 1 over 2 square root of x. Why is that? Because it's, 1/2 times x to the negative 1/2 is 1 over square root of x. So if that makes a difference, I can write it this way. I can find a common denominator, rationalize this fraction, and do other things, but I'm not interested. So I'm happy with this answer here, folks. I don't have to do this whole thing. But I just want to point out that no matter how complex these problems look, they really reduce to that one pattern, which is over and over emphasized here. And that's, and finally, our last thing today will be, and that's this is a kind of a power, more of a power function, more in line with what you will see in calculus 2. So this is, again, this is a complicated function. So here we go. So number 45 of 2.5. The function is y equals cosine of the square root of sine of tangent of pi x. All right, this function, how do you do the derivative of that? What's going on here? What is the power here? Well, there's going to be a power. That's the square root of x. But before you do that, you have to recognize that the structure of this, and this is why I pounded on you at the beginning of the hour and in the previous lesson with the structure as a composition of functions. So this is cosine of, and over here you have something, and this thing is this guy here, square root of da. So it's sine of tangent, if you want, of pi x, this guy to the 1/2. So this is the function. So it's a composition of cosine and that function. So when you do the derivative, folks, here, the derivative is going to be the derivative of cosine, the leftmost function in the composition, which is sine. So it's going to be sine of tangent of pi x times, and that's so it's times, not composite or anything, times, and then I'm going to do the derivative of the inside quantity. So the inside quantity, interestingly, is a power, is the 1/2 power of sine of tangent of pi x. So that's going to be 1/2 times sine of tangent of pi x, so that quantity to the negative 1/2 times, then I'm going to say the derivative of the inside quantity for this one here times sine of tangent of pi x primed. And look at that, even that is not finished, because I will have, and this is, folks, sine of, so you know this one here, I'm just copying the first two, sine of tangent of pi x times 1/2 times sine of tangent of pi x to the negative 1/2 times, and then with a sine of tangent of pi x primed itself is another chain rule. So it's again the leftmost sine primed, which is cosine of tangent of pi x times finally the derivative of tangent of pi x, which is secant squared of pi x times the derivative of pi x, which is pi. So there's a bunch of things here, really. There's a derivative after derivative after derivative. This is a super complex function. That's not realistic. You won't see this on a test. But I'm just showing you that you can apply you could end up in, at least in a theoretical situation, you could end up with a function like that where the derivative is extremely complex. Now I would say, and I'm gonna close the lesson here, folks. I would say that this is more on the artsy side of things. In practice, I don't think you will ever see this level of difficulty. In fact, in practice, what you will see, if you will attempt to sort of evaluate cosine of if you have something complex like cosine of sine of something, you would try to evaluate those in some other ways and do derivatives. So not with a chain rule because that will be extremely complex and convoluted. I'm pretty much done here, folks. I'm gonna stop the recording